Good morning, ladies and gentlemen. First of all, I would like to thank the chair of the conference for giving us this opportunity to present our paper. I'm Bhairavi Premnath, and on behalf of the authors, I would like to introduce our paper, a comprehensive analysis into the effects of quasiperiodicity on the swing equation. This work has been carried out since I started my PhD in mathematics at University of West London under the supervision of Dr. Anastasia Sofroniou just over 2 years ago. This paper is an expansion of prior work and builds on its conclusion to explain the concept of quasi-periodicity, focusing analytically and numerically the development of solutions whereby increasing the control parameter lead to a cascade of period doubling bifurcation before eventually losing its stability and exhibiting chaos. Basins of attractions is also studied within this research to understand quasi-periodicity. Stability in a power system is closely tied to the concept of disturbances, which are sudden or sequential changes through the system's parameters or operating quantities. Even a small disturbance can have an interesting and rich effect on the dynamics of a system. Linearizing the equation that represent a system, undertaking eigenvalue and frequency response methods that can be employed to study the stability of the system. In this study, a single degree of freedom system is considered, and that will allow for the study of nonlinear dynamics to be examined and to acknowledge even chaotic attractors. This study focuses on the nonlinear aspect of solid system using methods such as perturbation techniques and nonlinear methods. Initially in this study, an infinite busbar is represented with the assumption of constant voltage and frequency. So if a classical representation is considered, that is with a fixed voltage behind a transient reactant, then the busbar system is reduced to a second order differential equation, but with constant coefficient. As this resulting equation does not offer much interesting or novel information about the response of the system, the analogous swing equation is considered in this study. This includes parametric and external excitation, allowing for the techniques of perturbation theory to be employed under this new formulation of the extended busbar system. The swing equation studied here depicts the motion of the rotor of the machine as reproduced in the figure below. Considering the damping term, the swing equation that describes the motion of the rotor of the machine employed in this study is shown below in equation 1, equation 2, and equation 3. So here omega r is the constant angular velocity, h is the inertia, d is the damping, pm is the mechanical power, vg is the voltage of the machine, xg is the transient reactant, Vb is the voltage of the busbar system, theta b is the phase of the busbar system, and also Vb1 and theta b1 are magnitudes which are assumed to be very small. So after performing some mathematical operations on equation 1, 2, and 3, the following equation is obtained to carry out further analysis. Alpha 2, alpha 3, etc. are shown in this slide, and algebraic techniques such as Taylor expansion and substitution are undertaken to obtain this final equation that will be used for perturbation analysis. So what is quasiperiodicity? Quasiperiodicity refers to a form of motion that exhibits the presence of two or more frequencies that are not rational multiples of one another. This implies that the system does not quite revert to its original condition, although it does approximate it periodically. Quasi-periodic motion is frequently observed in dynamical systems that exhibit perturbations of integrable systems. An example can be found in the case of double pendulum, where the motion exhibits quasi-periodicity when the amplitudes are minimal. The concept of quasi-periodicity lacks a universally agreed upon description. Nevertheless, a frequency employed methodology involves the establishment of definition of quasi-periodic motion, whereby it describes a dynamical system that is classified as quasi-periodic when it possesses a solution that can be expressed as a combination of two or more frequencies that are not in a rational ratio with each other. So the importance of quasi-periodicity in the swing equation resides in the ability to generate chaotic dynamics. Chaos is a type of movement that is extremely sensitive to its starting conditions. It is evident that the two trajectories start off near to each other. The subsequent divergence follows an exponential growth over a specific duration. The presence of chaotic behavior requires a thorough comprehension of the fundamental variables because of its inherent unpredictability and difficult controllability. The significance of this phenomena also resides in its capacity to generate complex patterns. Empirical data also shows that using quasi-periodic solutions in the swing equation can generate spiral patterns which are normally found in natural systems. So to analyze the quasi-periodicity, we use the Hamilton's principle. Hamilton's principle is a fundamental notion in classical mechanics, and it is crucial for comprehending the dynamics of a physical system, such as the swing equation. It involves studying the system's Lagrangian and using the concept of stationary action. The swing equation characterizes the movement of the rotor, whereas the Hamilton's principle enables us to deduce the equation of motion by minimizing the action integral. Over time in quasi-periodic realm, controlled by Hamilton principle, the swing equation may undergo a shift towards chaotic behavior. Chaos occurs when the system's reaction becomes extremely responsive to the beginning condition, resulting in an unexpected and irregular movement. During quasi-periodicity, the shift into chaos is characterized by disruption of stable periodic orbits, the emergence of bifurcation, and the initiation of integrate non-repetitive trajectories. The system's susceptibility to disturbances, coupled with the incompatibility frequencies inherent in quasi-periodicity settings, leads to the swift progression towards chaos. So Hamilton's principles, which emphasizes the minimization of action and determination of system trajectory, is useful for comprehending how quasi-periodicity might work as a pathway to chaotic dynamics in swing equation over time. So using Hamilton's principle in equation 1, that equation was transformed to this following equation. Then this equation is used to plot the angle against time for the case of Hamilton's principle, and then comparing it with methods of strain parameters and Foucault theory for further analysis within the context of quasi-periodicity. So the graph depicts the progressive decline in stability over time, resulting in state of instability characterized by the quasi-periodicity. And over time, the system's movement becomes more irregular and unpredictable, demonstrating the system's sensitivity to the quasi-periodicity for all the methods considered. The observed behavior indicates that the intricate interaction between external forces and the inherent dynamics of the system might result in chaotic motion. So the equation 1, 2, and 3 was simulated on the digital computer by using the fourth order Ranjakata method, and the effect of varying the excitation frequency omega for the initial condition when VB is equal to 0.1 was studied in detail, and the representative results are shown in the next few slides. The phase portrait of the attractor forms a closed orbit when omega is equal to 2 pi radians per second, showing a torus phenomenon. This can be verified by observing the frequency domain plot and the Poincare map. As omega is decreased further to pi radians per second, the orbit changes qualitatively as shown in this slide. And when it becomes 2 pi by 3 radians per second, phase portrait still shows torus phenomena, signifying the movement of synchronous generator is not strictly periodic, but rather exhibits a more intricate torus-shaped configuration in the phase space. Now omega is reduced to pi by 2 radians per second, eventually showing a torus attractor. And then if it's further reduced to 2 pi by 8, the response of the system becomes unbounded, resulting in loss of synchronization and loss in stability. We also considered the golden ratio number, which is a irrational number, and equated that to the omega to see the behavior of the system. And the figure visually represents the influence of the golden ratio on the swing equation. The phase portrait offers a perspective representation of the system's trajectories and as it evolves over time, showcasing the changes in the system tilt and angular velocity. It also exemplifies the torus phenomena again, and Poincare maps provide a concise depiction of the system's behavior by showing where the trajectory intersects with a particular plane. Moreover, frequency domain chart facilitate the examination of the spectral characteristics of the system, revealing prominent frequencies and possible resonances. Utilizing the golden ratio in this analysis offers a distinctive perspective to see and comprehend the complex quasi-periodic patterns that arise in the swing equation. So there are three routes to chaos, which are given by torus bifurcation, cascade of period doubling bifurcation, and intermittency. Hence, the results from the above figures show a summary as omega is decreased in the system loses the stability and cascades towards chaos. As the value of omega is decreased, it can be observed that the graphs undergo dynamical transformation, including torus solution, and further reduction leads to chaotic attractor for the case of quasi-periodicity. Bifurcation occurs when a small change to a parameter value of a system causes a change in the behavior, whether it's topological or qualitative change. Bifurcation can occur in both discrete and continuous time systems, and it has an impact on the power system and related topics such as oscillations and voltage collapse. So the bifurcation diagram shown in this slide was constructed by solving the swing equation for a specific value of omega pi by 2 radians per second and by numerical time integration using the classical fourth order Ranjagata algorithm. The forcing R is incremented slightly and time integration continues plotting the maximum amplitude of the oscillatory solution versus R, where R is shown in this slide. Hence, you can see at around R approximately 1.9, the first period doubling in a sequence of period doubles is exhibited, leading to a chaotic behavior. This numerical analysis shows that the swing equation moves towards loss of synchronization as the value of R is increased. Using experiments and simulation, researchers developed the algorithms of Lyapunov exponents. The Lyapunov exponents give details about the behavior of the system, hence plays a vital role in the analysis. Here, the above bifurcation diagram is verified through this Lyapunov graph shown on this slide for the case of quasi-periodicity. It is observed that at approximately R is greater than 1.9, the chaotic region has commenced and the Lyapunov exponent has taken positive values. So now we consider stability reduction. The provided graph shows the stability reduction for the swing equation using Lyapunov exponents. In the first case, we consider the primary resonance frequency 8.27 radians per second. And the second case, we focus on quasi-periodicity, where we add a small irrational number closer to the primary resonance, and it becomes 8.27 plus 2 pi by 8 radians per second, which is an irrational number, to study the behavior. So this frequency is particularly chosen to illustrate an example of the behavior of the dynamical system. So the Lyapunov exponents can be used to analyze both primary and quasi-periodicity processes considered here, and changing the parameters VB1 in the swing equation may cause the Lyapunov exponents to vary, indicating transition between stability and instability. The graph illustrates how an increase in a parameter leads to a loss of stability by showing the change in the number of Lyapunov exponents for each case. Basins of attraction shows the stable and unstable regions and helps to analyze the changes made to the system. So the plot shows the changes in the basins of attraction when variables are altered. It is also necessary to consider the boundary condition when analyzing the basins of attraction. So the basins of attraction for the quasi-periodicity when variable VB1 and theta B1 are changed and considering the omega to be pi by 2 radians per second. As the variable is increased, the stability of the system changes, and the red and the green colors show the stable region, the other colors show the unstable regions. And as the variable is increased, the system enters a corrupt state with unstable region. Hence, a further analysis on the effects of the variables in the system should be considered for sound results in this study. So in conclusion, this paper highlights the dynamical behavior of the swing equation as control parameters are varied for the case of quasi-periodicity. The entailed work provides analytical methods, specifically perturbation techniques, which are compared with the numerical stimulation to verify the validity of the solution for the case of quasi-periodicity. The numerical analysis for the case of quasi-periodicity incorporating numerically constructed bifurcation diagram, Lyapunov exponents, phase portraits, frequency domain plots, and Poincare maps all confirm the torus phenomena in a sequence, triggers chaos, and is a precursor of imminent danger and difficult operations in practical system. Bifurcation diagrams can also detect pre-chaotic or post-chaotic changes in a dynamical system under different parameter variations and also analyze chaotic behavior. So this study's aim was to complement current literature of this model utilized in power systems, yet gaining a better understanding of the underlying swing equation. This research aims to improve control strategies and preventative measures for power systems by deepening the understanding of the fundamental principles. The focus on mitigating chaotic effects of quasi-periodicity benefiting the engineers and researchers should be the future work. And potential investigation of quasi-periodic situation integration into swing equation framework is suggested, and the aim is to enhance long-term stability and adaptability of power systems through improved understanding and advanced methodologies. These are some of the references used, and thank you for your time and thank you for listening.